Yo yo, what's up, chem people? Today we are going to start one of my favorite units, and this is called organic chemistry. So in regular freshman chem, we do a small unit on organic, but if it was up to me, we'd spend a lot more time on it. I love organic. Um, But in reality, your freshman chem, we don't spend too much time with this because if you're a chem major or a bio major or any type of science, major science major, you're gonna have to take organic chemistry by itself. So you could take up to 2 semesters of organic. Anyways, so we're just gonna kind of run through a little bit more than just the basics, but I'm gonna spend a couple weeks talking about some of these organic molecules. Now, originally, organic chemistry was defined as the chemistry of life. And originally, scientists thought that all organic compounds could only be made by living organisms, whether they were humans or any animals or plants or all of these different things. Right? It was originally thought all these organic compounds could only be made by these living organisms, hence why it was called the chemistry of life. Well, it was eventually discovered that we could make these organic compounds in the lab, and the definition of organic chemistry has changed, and it's really the study of the element carbon. And most carbon compounds, not all, most. So there are a couple so we have organic compounds, and then we have things that are called inorganic compounds. Now, mostly we've been studying inorganics, okay, so like our salts, our acids, okay, our ionic compounds. These are all our inorganics. Right? There are a couple compounds that have carbon in it that are inorganic. So, for example, carbon dioxide is considered an inorganic compound. It does have carbon in it, right, but it's not an organic compound. Carbonic acid, H2CO3, is another what's called inorganic compound. So there are a few. There are a few compounds that have carbon in it that are not considered organic compounds. These would be inorganic. Now, there are hundreds of thousands of organic compounds. Compared to the number of inorganic compounds. So, for example, right, if I have NaCl, right, that's an inorganic compound. I can't really just add to this. That's the compound. Okay, that's how it comes together. It's a salt. Right? But in an inorganic compound, or excuse me, an organic compound, we have these carbon chains. So let's say we start with this. Well, if I take this one H off and replace it with, I don't know, a fluorine atom, that's a different compound. Okay. If I move this fluorine, so if this was an H to here, that's a different compound. If I move it over to here, that's a different compound. If I move it over to here, it's a different compound. Okay. What if I leave this one and I add another fluorine here? That's a different compound. All right, so it's really, really easy to make different organic compounds. That's why there are so many of them, right, compared to our inorganics. So why is organic so important? Why? Why? Well, it really comes down to the carbon atom. So in our carbon atom, it's got 4 valence electrons. And because of the way it can move these electrons around and hybridize, it's very versatile. Right? It can do lots and lots of different things. It can form lots of different types of bonds. So in a carbon atom, we can form 4, it wasn't on the screen there, sorry. I can form 4 single bonds. Which gives us that typical tetrahedral shape. And when the carbon atom forms that 4 single bonds of that tetrahedral shape, it goes through sp3 hybridization. So it can form 4 singles. It can form 1 double and 2 singles. And when it does this, it goes through sp2 hybridization. It can form 1 triple and 2 singles. It can form 2 doubles. Anyways, it can form all these different numbers of bonds, and it's one of the very few atoms that can do this. Right? That's what makes carbon so diverse. Right? And it's a great building block for life because it can do all these different things. So now these carbon atoms, okay, they're not like our inorganics. Our inorganics form small molecules or they network together. Carbon atoms tend to do something different. So our carbon compounds tend to form long chains and rings. Now, in your original chemistry class, you probably spent most of your time talking about long chains. Right? And again, we're going to spend most of our time talking about long chains, but we are going to talk about rings also, a little bit more. So when we're talking about these long chains, okay, we're talking about carbons that are in a row, and this is called the carbon backbone. Okay, so carbon attached to a carbon, attached to a carbon, attached to a carbon, attached to a carbon. All right, and these would all have hydrogens on them. So this is an example of a carbon chain. Well, they like to make rings also. Okay, so this is an example of a ring it could make. Okay, so you get this ring like this, and this would have hydrogens off like this. Okay, so this is what's called a ring structure. Now, what's pretty cool, and we're not going to spend too much time with this, but when you take organic chemistry, these end up, chains will often fold up into rings. So what will happen a lot of the times, and you'll learn this relationship, is that okay, it may start as a chain, but you may have some sort of equilibrium where you have this both a chain and a ring. So this would fold up, and we got a 1, 2, 3, 4, 5, 6 carbon chain. 1, 2, 3, 4, 5, 6 carbon chain. So this will actually fold up, okay, and it'll go into that ring. Or this ring will unfold and go into a carbon chain. We're really not going to spend time, we're not going to spend time talking about this, but this is something that you'll eventually talk about in organic chem when you take it in college. Right, so you have this chains turning into rings and rings turning into chains. Pretty cool stuff. All right. Let's, I want to review real quick a little bit about intermolecular forces. So, most of these, most of our organic compounds or our hydrocarbons are nonpolar molecules. Okay, so if it's a hydrocarbon, it has hydrogen and carbon only. Alright, so if they're nonpolar molecules, that means they're held together with our London dispersion forces. And we've talked about this many times. Okay. So, if we're comparing two carbon chains, let's see, we're comparing this one, and we're going to compare that one. All right, we know that this one's going to have more dispersion forces. Okay, if there are more dispersion forces between the molecules, that means this is going to have higher melting and boiling points. More dispersion forces, higher melting points and boiling points. Right? And we've talked about that. Now, there's a relationship between the length of a carbon chain and its intermolecular forces. So, the longer the carbon chain, oops, the stronger the dispersion forces, the higher the melting and boiling points. And none of that's new. We've talked about that multiple times. Now, if there are side chains, it changes this a little bit. And by side chains, I mean this. So instead of just a straight 4-carbon chain, let's say that there's this side chain coming off of it. Well, what that does is it's going to interrupt our dispersion forces a little bit. All right, so now these dispersion forces here and here and here, since the molecules are further apart, those weak forces are weaker. All right, so these can't come together as close as if we were up here. Okay, so these would be closer, so the dispersion forces are stronger. All right, so adding side chains is going to decrease our dispersion forces, and it will lower our melting and boiling points. And again, this is something we've already talked about, but I wanted to make sure we got that in this discussion. All right, so it's in your notes here. All right. Let's get down and dirty into some of this stuff. All right, so the first thing you need to memorize are prefixes for organic. All right, so you need to know these prefixes, and we're only going to go through 10, and some of them are, you know, they're not hard, they're pretty simple, and most of them you'll know. And we're going to need this for naming and numbering carbon chains and things like that. All right. So 1, the prefix we're going to use is meth. 2 is F. 3 is prop. 4 is bute, not but bute. 6, oops, I missed 5. Having trouble counting this morning. So 5 is pent. 6 is hex. 7 is hept. 8 is oct. 9 is known. And 10 is dec. If you don't know these yet, you need to memorize them now. Okay, so memorize these. You're going to need them. All right. So we're going to be using this as we talk about all of our organic compounds. We're going to be using these prefixes. So let's get into our what are called our first homologous series. And when we're talking about homologous series, this is a series or a group of hydrocarbons with similar properties. Okay, so we take, as scientists, if we have a large amount of material or a large amount of information, what we do is we like to organize it. All right, and this is what we're doing for our organic chemistry. We put these different types of organic compounds into groups, and those groups are called homologous series. Now, when we're talking about hydrocarbons, we're talking about a very specific part of organic chemistry. All hydrocarbons are made up of only hydrogen and carbon molecules, atoms, excuse me. Okay, so hydrocarbons are only hydrogen and carbon. So as soon as you put something else on it, like a fluorine or a chlorine atom or an oxygen or a nitrogen, they're no longer hydrocarbons. So we're going to start with our hydrocarbons. Now the first homologous series we're going to talk about are called the alkanes. Alknes. And these are also called the paraffin series. And some of you may recognize that word paraffin. And these are a lot of our waxes. Okay? A lot of our candles are made out of paraffin. All right, and it's a hydrocarbon. So in the alkanes, these are all what are called saturated hydrocarbons. And what that means is that all the carbons have all single bonds. There are no double and triple bonds. All right, so let's see. This would be an alkane. Now, this is this is just the backbone. All right, so this is the carbon chain. There would be hydrogens coming off of all of these, but I've left them off just so we can see. All right, so this is an example of an alkane. How do I know it's an alkane? Because it's made of all single bonds. All single bonds. Now, all right, we'll come back to this. The name for these always end in ane. A-N-E. The general formula for this for the series, the homologous series, is C to the N, H to the 2N plus 2. Okay, the N stands for the number of carbons in the molecule. So what this does is it will give us our molecular formula. Oops. So if I know the number of carbons, I can quickly figure out the molecular formula of that alkane. All right. So let's start with this guy. Okay. This is a 4-carbon chain with all single bonds. All right. So let's start by drawing the structural formula. Okay, and you always start, when we're drawing structural formulas, you're always going to start by drawing the carbon backbone. All right, so the carbon backbone is just 4 carbons in a row. And we're going to draw them straight. All right, I know it's not straight, that's actually zigzagged, all right, and this is more of what it looks like, but when we're drawing structural formula, we want it as simple as possible. All right, and we realize that that's not what it actually looks like, but that's okay. All right, now, once we have the carbon backbone, we have to fill in the hydrogens. And to do it, you have to count. I'm telling you right now, you have to count. Carbon is going to want to make 4 bonds and 4 bonds only. So to fill in our hydrogens, we're going to count. So this carbon right here has 1 bond. So it's going to need 3 hydrogens to make a total of 4 bonds. This carbon has 2 bonds already. We're going to add 2 hydrogens to fill out the tetrahedral. This one has 2. This one has 1, so we're going to add 3. So this would be my structural formula. All right, now this is longhand. Okay, and I expect you to use longhand, but we use a lot of shorthand also. All right, so this would be the same thing. If you have bonds off a carbon, that there's nothing on the other side, so like there's no element here. It's assumed that there are hydrogens on the other side. All right, so this is called shorthand. Yes, you can use this in homework. Yes, you can use this in your notes. You cannot use shorthand in labs or on a test if I need you to test on this. Okay, so you're going to use longhand for labs. All right, but we'll use lots of shorthand. Okay. All right, so this is the structural formula of this guy. Now, what's the molecular formula? Well, we could sit here and we could count all these up. So I could count how many carbons, and then we can go and count how many hydrogens. Or we can use C to the N, H to the 2N plus 2. Okay, we know we have 4 carbons, so it's C4. H would be 2 times 4 plus 2. Well, 2 times 4 is 8, plus 2 is 10. So this would be C4, H10. This is molecular formula. Then there's something called the condensed structural formula. And the condensed structural formula is kind of a combination between the structural formula and the molecular formula. Right? And to do that, we do it this way. We start at one end, and we look at the first carbon, and then we figure out what's coming off of it. So this is carbon 1, and it's got 1, 2, 3 hydrogens. So this would be CH3. Then we go to our second carbon, okay, and there are 2 hydrogens coming off of it. Then we go to our third carbon, and there are 2 hydrogens coming off of it. Then we go to our fourth carbon, and there are 3 hydrogens coming off of it. So this would be CH3, CH2, CH2, CH3. Okay, so this would be our condensed structural formula. All right, well, last thing we want to do is we want to name this. When we go to name, you always find the longest carbon chain, or the backbone. Always. Okay, now this one's pretty simple. It's 4 carbons in a row. 1, 2, 3, 4. Okay, just straight 4 carbons in a row. So the prefix for 4 would be bute. This has got all single bonds. It's saturated, so that's an ane. So this would be a type of butane. Now, if it's just if it's an alkane and it's just straight carbons all across it, all right, all single bonds, straight chain, we say that this is N-butane, which stands for normal straight chained butane. Okay, yes, you'd have to include that N. So this is normal butane. Right? Now, let's break this up. So the N tells us that we're straight chained. The bute part tells me 4 carbons in a row. The ane part tells me all single bonds. So this is an example of normal butane. 1, 2, 3, 4 carbons. All right, let's do another one with our alkanes. Let's do normal N-heptane. All right, so let's break this word down. The N tells us that it's straight chained. Hept tells me that there are 7, oops, not 2, 7 carbons. And the ane part tells me all single bonds. All right, so let's come up with our molecular formula. Well, it's C to the N, H to the 2N plus 2. So we know we have 7 carbons, so this is C7. H, well, 2 times 7 is 14, plus 2 is 16, so this is C7, H16. All right, well, let's draw it. Okay, let's draw my structural formula. Well, we need 7 carbons all in a row. 1, 2, 3, 4, 5, 6, 7. Okay, 7 carbons in a row. They have all single bonds, so I put my single bonds in, so we're good there. Right, now I have to go back and I have to fill in my hydrogens. I do it by counting. Right, so this one only has 1, so it's going to need 3. This one has 2, so it needs 2. This one has 2, so it needs 2. This one has 2, so it needs 2. 2, it needs 2. 2, it needs 2. 1, it needs 3. All right, so I used shorthand, so we assume that there are hydrogens all out here. Now, my structural formula better match my molecular formula. I better have 7 carbons and I better have 16 hydrogens. So let's count. 1, 2, 3, 4, 5, 6, 7 carbons. Hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And they match. Alright, so there's my structural formula. Let's write my condensed structural formula. We're going to start right here with C, and it's got 3 H's. CH3, CH2, 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 1, 2, 3, 4, 5, 6, and CH3. Now, what you will see sometimes is they will condense parts of this. You know, so you could actually see this. C3H7, CH2, C3H7. Okay. I don't want you to do this, but you might see it. Now, the CH3, the C3H7, excuse me, is just condensing that part. Boop. And that would be my CH2. And then this is just putting this together. Alright, so you might see something like that. Alright, but I don't want you to do that. Now, I want to show you something else. These two things are exactly the same thing. Okay? And let me put it together for you. There's one more. Here it is. It doesn't really fit on the screen, but that's okay. You can see what we're doing here. So if we look at the 7 carbons in a row, is this what the molecule actually looks like? And the answer is no, all right, because you got this zigzag pattern.